Okay, continuing with section 2.2, we were in problem number 11, and I had gotten the graph done. Now I was moving on to part B, where we were going to do the range of the function. So what you're going to do is you're going to determine the range, which are the y values again. You're going to determine the range of each piece separately, and then you're going to give the final range for the entire problem. You're going to union the two ranges together. So on the right-hand side, the range, which is the y values, those y values go from 2 to infinity. Okay, this is for the right side. And then for this left side, this graph goes as low as 0 for the y values, and then as high as positive infinity. And you're going to union these together. And this is actually supposed to be a bracket, because right at 0, that's an actual point right on the graph. It's not, I got my eyeballs on this hollow part right here, and I'm not concentrating. So that point right there is a point that's right in the middle of the graph, and it actually runs right through that point, so it should be a bracket. So anyway, your final range on this problem is where you union these together. And if you put all these numbers together in one set, they go from 0 all the way to infinity. Okay, so that would be your range for that problem. And that is part B. The graph, all of the graph was part A. Okay, moving on to problem number 11, where I believe you're doing the same thing. Okay, so in problem number, oh no, actually that was 11. Problem number 12, you're doing the same thing, which is to graph the function and then also determine the range at the end. Okay, so now this time the wall is at 4. Notice that both of these specifically talk about -4. So you're going to drop that vertical wall right at -4. And you're going to graph these one at a time. Now, these are both straight lines because they're both first degree. And you can just get 2 points for each one. You could also graph this by y-intercept and then slope. I'll just do it by points. So when you go to graph this first one, again, remember, you're anchoring right to the wall. You have to anchor that graph to the wall. So we're going to start with a -4 value in the top graph, which is called x plus 3. We're going to plug that anchor value in there on the left as well as the right and get the y partner that goes with it. So that's -1. When you plot this as a point, you plugged in -4, you got -1 as a y partner. Now, because there is no little equal sign here, when you go to graph this, this is going to be an open endpoint. Okay, that's because of that right there. Okay, so go plot -4, -1. That's going to be right down here. I'm going to erase part of the line just so it doesn't look like it's a closed-in point. And there is my open hollow point. Again, these are straight lines. I need one other point to connect to that hollowed out point. So I'm going to obey what this restriction says, that I should stay less than -4. I mean, the first value has to be the actual value at the wall so you can anchor in to that wall. So now things that are less than -4, -5. Things that are to the left of -4. Go plug into the function, which is x plus 3. Put that -5 in there. And you have another point to plot. You plugged in -5, you got -2 for an answer. So go plot that now. Okay, -5, -2. Here's another point and connect. So there's one of your graphs, one of your pieces, and now go graph the other piece. The other piece is defined by x minus 3. So now, again, we're going to anchor into the wall right at -4, only using the other function, which is x minus 3. So we're plugging in right now the anchor value so we can hook into the wall. -3, that's equal to -7. As a point, that would be, I plugged in -4, got a -7 as my y value. When I go to plot this point, I'm going to make that anchor point colored in, and that's because it goes with this information right down here, and you see there's a little equal sign there. So that point is solid. So go plot -4. This will be a solid point. So -4, -7. It's going to be, let's see, let me get this out of the way. I'll move it. So -4, -7, that's going to be -6, so it'll be about down here somewhere. -4, -7. And I'll just fix this a little bit. So about right there. Now, I want to remind you that if you were doing an entire graph, this line would continue up this way, just as all graphs do. They climb. All lines that have a positive slope, they continue upward and to the right. But it just like crashed into the wall and did not have the ability to continue because it's just, you're only doing a piece of a graph. Same thing with what's going on right now. So now I'm going to do another point. I did one right at the wall. I'm also going to do it at x equal to, let's see, I'm supposed to be using values that are greater than -4. That means on the right side of -4. So greater than -4 would be values over here. So you could use -3. You could even use 0 if you want to. I'll plug in -3. So it's f with a -3 plugged in. The function I'm plugging into is x minus 3. So -3 minus 3, that's equal to -6. And now I have another point to plot, which is -3, -6. Okay. So continuing with that, go plot that point. -3, -6 is about right there. So you can see that here is your line on the other side. Okay, so you have one line that's over here, and then you have another line that's over here. Okay, then we're on to part B, where we talk about the range of each point. So talking about the range of the leftmost piece, that piece, it goes as far down, I mean the y values go down as far as -infinity. And those y values go as high as, let's see, that would be -4. So -infinity. And that this y value right here, actually I'm looking at the -4 for the x value. That y value that goes with that is actually -1, because on the y-axis they're counting in ones. So the y values down here are -infinity, and then the very highest y value on this little pink line right here is a y value of -1. Okay, so that's the left side. And then the rightmost piece, that graph on the right side of this line called x equal to -4, The very lowest value you have with respect to the y values is, it was negative, this was down at -7. And then that goes as high as positive infinity. So now when you go to do the final range, you're going to do the union of those two. So it's going to be negative infinity all the way up to and including that y value, which is -1, union together with -7 to infinity. So when you put all of these together, these would be all the numbers up to -1. And then these would be the numbers from -7 to infinity. So this would be from -infinity to infinity. Okay, last problem. Now we're going to be doing the difference quotient, and I just want to mention that the difference quotient is really just the slope. So you can use that as kind of a way to check your answer. And when you're checking your answer, it should come out to be, after you do all of this, it should come out to be whatever the slope is. The slope, remember, when you're looking at a linear equation, y is equal to mx plus b. So that's what a difference quotient is. It's really the slope. So now when we go to do these problems, it's going to be, we're going to follow this. You're going to show the work for this. This is a very important concept, especially if you're going on to take any classes after MAC 1105, which plenty of you will attempt to do that, because the majority of what you study is connected to slope in all of the classes that come after this. Is heavy application of that in pre-calculus as well as calculus. So when we're doing this, we're going to follow what this says. It says, take the function and plug in x plus h. Take the function, plug in x plus h. Then also take the function and plug in just x. In other words, the original function, and subtract what you get when you do both of those things. So let's do this part first. Let's take the function, and everywhere there's an x, we'll plug in x plus h. Okay, here's your function. This says that instead of f of x, that everywhere there's an x, you should plug in x plus h. This is what you're plugging it into. So it's -3x plus 2. I left a blank spot where the x is, so you can plug in x plus h. So there is the function with an x plus h plugged into it, just like this says. Now we're going to subtract, and when you're going to subtract and there's more than one term that's going to come after the subtraction sign, you need to close it off with parentheses or brackets, either one, just so you'll remember to switch the signs. Now it says subtract, we got the subtraction sign, the original function, just f of x, which is -3x plus 2. So you don't have to plug anything in. That's just the original function. Okay, this portion right here is called f of x plus h. This portion right here is called f of x. And then all you have on the bottom is just h. Okay, so let's get this worked out on the top. It's -3 times x, then -3 times h, then plus 2, then opposite of -3x, positive 3x, opposite of positive 2, -2, and that's all of your top over h. Continue simplifying in the numerator. In the numerator, you have -3x and positive 3x. Those cancel. You have positive 2 and -2. Those cancel. So you're left with -3h over h, and that equals -3, which is what I was telling you. the difference quotient, which is what we just did. We took the